Hello everyone. Recently, we have come across an article published in Science Alert that says, "Sound of the Big Bang suggests our galaxy floats inside a void." So what they are saying is that our Milky Way galaxy, along with Earth and everything around us, is actually drifting inside a gigantic bubble of emptiness in space. So we started to dig deeper into this topic while maintaining a central question in our mind. Is this true? Well, after continuing our research, we have discovered a potential answer. Maybe it is. Before we get into voids and sound waves, let's talk about this Hubble tension that has astronomers so worked up. So the universe is expanding at a faster rate. If we measure the expansion rate, called Hubble constant, using the early universe's afterglow, things like the cosmic microwave background, which is the faint thermal radiation left over from the early universe, released when the universe cooled enough for light to travel freely, offering a snapshot of the cosmos just 380,000 years after the Big Bang. By analyzing the cosmic microwave background or ancient sound wave patterns, scientists estimate the universe's expansion rate to be about 67 kilometers per second per megaparsec, meaning that for every 1 megaparsec, roughly 3.26 million light-years away from us, a galaxy appears to move 67 kilometers per second due to cosmic expansion. So basically, for every 3.26 million light-years of distance, space expands by 67 kilometers per second. So the speed of expansion increases with distance. For example, a galaxy 3.26 million light-years away moves away at 67 kilometers per second. A galaxy 6.5 million light-years away moves away at 134 kilometers per second, and so on. So getting back to the topic, if we measure the space expansion rate using cosmic microwave background or ancient sound wave pattern, we get 67 kilometers per second per megaparsec. While if we calculate the expansion rate by looking at relatively nearby objects like exploding stars, type I supernovae, or pulsating stars, Cepheid variables, we get about 73 kilometers per second per MPC. So looking at these two, you can see these numbers does not match right. This conflict between measurements is the Hubble tension, and it's been called the most exciting crisis in cosmology because it might hint that our understanding of the universe's physics isn't quite complete. And this is where it all begins. So till now we learned only about what is Hubble tension. So now let's get into our main topic. As you remember, the article states sound of the Big Bang implies that our galaxy is floating within a void. So how does the scientists are proving we are inside a void just by the sound of Big Bang? What is that? And how can we hear, or rather see it today? Well, we're referring to something called Baryon Acoustic Oscillations, or BAOs for short. Despite the fancy name, the concept is beautiful and simple. BAOs are basically fossilized sound waves from the early universe. Right after the Big Bang, the universe was extremely hot, dense, and filled with a plasma. Imagine a vast, glowing soup of particles. In that primordial soup, sound waves could travel. Any little disturbance would send pressure waves rippling through the hot plasma, kind of like sound waves moving through air. These are the original sound waves of the Big Bang. And if you were magically there, you'd hear a tremendously low rumble or cosmic sound rolling through the infant universe. Now, as the universe expanded, it also cooled. At about 380,000 years after the Big Bang, it cooled enough for atoms to form and light to travel freely. This is when the cosmic microwave background light was released. At that moment, something important happened to our sound waves. The medium, the plasma, became too thin to carry sound, so the sound waves froze in place. A great way to picture this is like stirring a bowl of jelly as it sets. The ripples you create stay locked in once it solidifies. In the universe, these ripples became permanent imprints in the structure of matter, forming huge, faint rings of galaxies and gas clouds that are still visible today. These frozen wave patterns, the BAO rings, are spaced about 1 billion light-years across. That's the scale of the original sound waves. Today, astronomers can detect them by studying how galaxies are distributed across the universe. They find that galaxies are slightly more likely to be separated by this exact distance, evidence of those ancient ripples. BAOs give us a standard ruler for measuring cosmic distances. Since we know the actual size of these waves, we can compare how big they appear from Earth. That tells us how much the universe has stretched over time. In other words, how fast it's expanding. So yes, these faint echoes from the early universe still guide modern science. That's why BAOs are often called the fossilized sound of the Big Bang, because they began as literal sound waves and left behind a pattern that shaped the structure of the cosmos. Here's where things get really interesting. If our galaxy is sitting inside a giant cosmic void, it could actually bend or distort the way we interpret the universe's ancient sound waves, those BAO ripples we talked about earlier. Normally, BAOs act as a reliable measuring stick for how fast the universe is expanding. But if we're in an underdense region, a space with less matter than average, then gravity works a bit differently. Inside the void, galaxies, including ours, would feel a stronger gravitational pull from the denser regions surrounding the void. This would give them a little extra outward push on top of the normal expansion of space. As a result, when we observe distant galaxies and measure their redshift, how much their light has stretched, they may appear more redshifted than expected because they're not just drifting with the cosmic flow, they're being nudged outward by this void-induced effect. In simple terms, the void makes it look like the universe is expanding faster than it actually is. So when we measure the expansion from inside this bubble, we get a higher value, around 73 kilometers per second per MPC. But someone measuring from a more average, less denser region might get the usual 67 kilometers per second per MPC. This local gravitational effect could explain the Hubble tension without needing any new or exotic physics. This is a huge shift in how we might solve one of the biggest puzzles in modern cosmology. It suggests we may not need to rewrite the laws of physics or invent mysterious new particles or forces to explain the expansion rates. Part of the answer might simply be that we live in an unusual part of the universe, an oversized cosmic basement, so to speak. As the Science Alert article cleverly put it, it's like finding the solution in nothing, the nothingness of space around us. This topic might seem a bit tricky to grasp at first, which is why we've explained everything in simple. Also, we've focused only on the key concepts and terms directly related to this content, giving you a broad understanding without going too deep. If any part feels unclear, feel free to re-watch the video. That's all for today.